System design. You have heard the term. Maybe you have been asked about it in an interview, or you are trying to figure out how Netflix serves millions of people without crashing. What does it actually mean? Let us start from the beginning. System design is the process of deciding how a software system should be structured so it can meet its requirements at the expected scale. It is more than drawing boxes and arrows. Good system design means understanding what a system must do, how data moves through it, which components own which responsibilities, where it might fail or slow down, and most importantly what trade-offs you are making. At its heart, system design is about making trade-offs under constraints. If you need very low latency, you add caching or serve data from edge servers closer to your users. If the system must stay available during failures, you add redundancy and automatic failover. If writes are growing too fast for a single database, you partition the data across multiple machines. There is rarely one perfect design. A good design is one where the choices match the problem. Here is a common mistake, starting from the technology. Let us use Kafka. Let us use Redis. Let us use Kubernetes. A much better approach is starting from the requirements. What does the system actually need to do? Once you understand that, the technology choices become clearer. We need to handle high write volume, absorb traffic spikes, and process events asynchronously. That points toward a queue-based system. So what does a system design conversation actually cover? There are 9 recurring questions that every good design discussion revolves around. Requirements: what should this system do? What is explicitly out of scope? Scale: how many users, how many requests, how much data? Data: what are we storing, where does it live, and how do we access it? APIs and communication: how do the different parts of the system talk to each other? Reliability: what happens when something inevitably fails? Performance: which latency and throughput numbers actually matter? Consistency: which operations need to be strongly correct, and where can we accept eventual consistency? Operations: how will we monitor, debug, deploy, and evolve this system? And cost: is this design reasonable for the expected traffic and business scale? The same product can have drastically different designs depending on its constraints. A chat app for a small internal team is not designed the same way as WhatsApp. Most systems are built from a small set of familiar components. At the edge, you have the client, a web browser, a mobile app, or another service making requests. Behind that sits a load balancer, which distributes incoming traffic across multiple servers so no single machine gets overwhelmed. Then come the application servers. They run the business logic, coordinate reads and writes, and orchestrate the workflows. To speed things up, you add a cache. Frequently accessed data lives here so you do not have to query the database every time. Speaking of the database, that is where durable data is stored. It is the source of truth. For asynchronous work, you introduce a message queue. Producers publish events, consumers process them later. This helps absorb traffic spikes and decouples different parts of the system. Workers pull from the queue and do the heavy lifting, processing images, sending emails, running analytics. And wrapping around all of this is observability, logs, metrics, traces, and alerts that tell you what is actually happening in production. But system design is not about listing these components. It is about explaining how requests and data actually flow through them. When a user opens a feed, does the request hit a cache first? If it misses, which service queries the database? Is the feed computed on read or pre-computed on write? Those choices are the real design. So how do you actually approach a system design problem? There is a simple 5-step process. Step 1: clarify the requirements. Before choosing an architecture, understand the problem. What are the core features? Who are the users? What scale are we designing for? Requirements decide the architecture, not the other way around. Step 2: estimate the scale. Get rough numbers, reads and writes per second, storage growth, bandwidth, peak traffic. The goal is not perfect math, it is identifying design pressure. A system handling 100 writes per second and one handling 1,000,000 per second will not have the same bottlenecks. Step 3. Start simple. Begin with the smallest architecture that could work: client, API layer, application service, database. Then add components only when there is a clear reason. A cache helps when the database is overloaded. A queue helps when work can happen asynchronously. Replicas help when read traffic grows. Partitioning helps when data no longer fits a single machine. Step 4. Identify bottlenecks and failure modes. What happens if the database goes down? If traffic suddenly spikes 10 times? If the cache is empty? If a queue consumer falls behind? A good design acknowledges these scenarios and explains how the system behaves when they occur. Step 5. Explain the trade-offs. Every meaningful choice has a cost. Caching adds invalidation problems. Replication adds consistency lag. Sharding makes queries harder. Asynchronous processing means users do not see results immediately. Cover both sides, why a choice helps and what new problem it creates. Now, it is worth noting that system design in interviews is not the same as system design in real life. In an interview, you have 45 minutes to work through an ambiguous problem at a high level. You clarify the scope, pick an architecture, and roughly reason about scale and trade-offs. In real life, it is an ongoing process. Teams design, build, measure, learn, and revise. You deal with legacy code, team ownership, budgets, migrations, compliance rules, and operational history. But the fundamentals are the same in both settings: understand the problem, start simple, identify the pressure points, and justify your choices. So to sum it up, system design is the skill of turning requirements into an architecture that can handle real-world constraints: scale, latency, reliability, correctness, operations, and cost. Understand the problem first, then choose the components. Start simple, identify the pressure points, and justify every trade-off. And remember, there is rarely one perfect design. A good design is one that matches the problem. If this was helpful, consider subscribing. There is a lot more to cover: CAP theorem, caching strategies, database partitioning, and more. Thanks for watching, and I will see you in the next one.